Okay, good morning, everyone. 9 a.m. and we can continue. All right. Okay, so in the previous lecture, we started introducing the world of magnetism. We started moving into that new world, right? And first of all, only a moving charge can produce magnetic field, right? So as I told you, everything is in dynamics in the world of magnetism. So if you have stationary charge, it will never produce magnetic field. It must move. Only when it moves, magnetic field will be produced around charges. If the charge is stationary, of course, electric field will be there, right? But no, not a magnetic field, right? It must move in order to produce magnetic field, right? So as a result, we can identify three systems which produce magnetic field. So the first one, of course, point charge moves. Of course, there will be magnetic field. We use symbol B to denote magnetic field. Then, of course, bunch of charges drifting in the same direction, identical charges, right? Current. Current will produce magnetic field. Most of the time, we're going to use, of course, this system to discuss and find magnetic field. And the last system, a permanent magnet. Right, permanent magnet, south pole, north pole, right? Of course, this system also produces magnetic field. And of course, if you ask where are the moving charges, we discussed it in the lecture. Orbital electrons, right? Inside of each atom, there are tons of electrons which orbit around nucleus. Yeah, those orbiting electrons, moving electrons, of course, under certain conditions can produce a non-zero magnetic field, right? Okay, so now, once we know that there is a magnetic field, of course, next question, what can be used to detect magnetic field, to probe magnetic field, right? So we need to come up with a convention about a probe system. And we agreed, of course, it must be some kind of permanent magnet. And where do we have some reasonably available, simple, small permanent magnet? Compass needle, right? So compass needle, that's our probe system. All right. Let me write it, compass needle, right? Okay, so of course we can draw a compass needle. It will be something like this, right? And of course, one side is the North Pole, and this is South Pole. And then direction of the North Pole give us a direction of the magnetic field. So for this, if, for example, compass needle arranged itself like this in the presence of the magnetic field, then this is a direction of the magnetic field at the point where you position this compass needle. So North Pole gives us direction of the magnetic field. Then, okay, so now we have a probe system, and of course now we can probe magnetic field created by any system, right? And of course we can introduce what is called magnetic field lines. The idea behind the magnetic field lines is almost identical. Actually, I wanted to say identical. Yeah, I would say identical to the idea behind the electric field lines. I will just repeat exactly the same words, but I will replace electric field with the magnetic field, right? Okay, so magnetic field lines, right? Probably, okay, let me draw first a picture. Right. So let's do it for a permanent magnet, right? So let's say, no, let me make it bigger. All right, actually thicker. Right. So let's say this is our permanent magnet, south and north poles, right? And so now if you use compass needle, of course, you can probe magnetic field, find the value of the magnetic field and direction at any point. And first of all, before I even draw the first magnetic field line, we have to tell something special about the magnetic field lines. All the time, they form closed loops. It's a consequence of the fact that there are no magnetic monopoles. No one has ever observed them. Of course, it wasn't the story in the world of electricity, because in the world of electricity, we had monopoles. Positive positive charge, what is that? It's a effectively positive electric monopole. And electric field lines started on the positive charge. Negative charge, it's a negative electric monopole, and of course, electric field lines ended on the negative charge. But now, since you don't have monopoles, so these magnetic field lines form closed loops. There are no any points where they can start and where they can end. All the time, magnetic field lines form closed loops. Okay, so let me draw something like this first. The first magnetic field line, and it gets close to the magnet. All right, and it looks like that magnetic field lines start at the North Pole, ends at the South. But again, it looks like because they are closed. They are closed in this case uh, through the magnet, right? Okay, so it looks like. So they start on the north and end at the south. And here I can draw something symmetrically position, right? Something like this, right? Okay, distorted. And then of course I can draw more. And here, right? And then maybe a few which goes to something like this. And there. And of course, as I said, they are closed through the magnet, gets close to the magnet. Okay, so magnetic field lines, very useful idea to analyze magnetic fields. Then, of course, how can we get information about the magnetic field? Magnetic field lines useful, but at the end of the day, you want to know information about the magnetic field. And story is identical to the story which we saw in the world of electricity. So if you want, for example, to find direction of the magnetic field at that point, completely arbitrary point, magnetic field is tangent to the magnetic field line. The same we saw in the world of electricity, right? So this is a B, right? Tangent to the magnetic field line, or over here, right? If I take this point, so this will be a magnetic field, right? Or over here, I can take, for example, this point. So again, magnetic field is tangent. Then what about direction I showed? What about strength, magnetic field strength? The same in the density of lines, right? So if over here density of lines is larger, magnetic field strength is longer. Oh, is stronger. Is stronger. Sorry. All right. So B stronger, and here, of course, B will be weaker. Right. Density of lines smaller. Magnetic field is weaker. Right. Maybe, you know what, in order to be sort of consistent with what I just described, yeah, I should have drawn this vector longer and this is shorter. Okay, let me do it. Let me fix it. Because otherwise it's just not consistent with what I am telling you. Right. So density of lines larger, so magnetic field strength must be longer. As a result, magnetic field vector must be longer. Then what else? Yeah, maybe I should also draw, if, for example, you position over here a compass needle, right? Of course, this should be your north pole of the compass needle, right? Because as I showed over there, direction of the north pole give us direction of the magnetic field. So. Okay, so now after these basic ideas about the magnetic field and world of magnetism, we need to introduce some expressions. And first we started introducing the expression. Basically, it's a fundamental law. It's a fundamental law which allows us to find magnetic field created by a wire. The story with the charge, more complicated. We're not going to touch that much. All right. Okay, so now a new bullet. Let me put it here. And of course, that is Biot-Savart law. Fundamental law. Okay, so and for a current, Biot-Savart law, let me add also for a current produced by a current, right? Okay, so let's assume that we have some wire. Right? It doesn't have to be straight at this point. And so let's assume it has a direction, a current has direction, this direction, right? And let's say we want to find magnetic field at some arbitrary point P, this. So what do we have to do? First of all, we need to pick infinitesimally short section of this wire. You know what, let me probably use different color. This, right? So ds. We have to write the expression which gives us a magnetic field at this point produced by a short segment, because different parts of the wire are in different conditions, right? So we cannot write the same for every section. So we need to take arbitrary section and write an expression for the magnetic field produced by only that section. Okay, so ds, you see, I introduced it as a vector. What determines the direction of this ds? Direction of the current. Direction of the current all the time determines the direction of ds. Right, then, of course, we will need a distance from that segment to the point where we want to find magnetic field, r small. And also, we need to introduce a unit vector which give us a direction. Again, the role of the unit vector, you see r hat, a small hat on top. The role of that vector is just to show that, okay, the point in which we want to find magnetic field is in that direction or that direction. That's the only role. It gives us a direction. Magnitude of r hat is 1 all the time. You remember unit vector. So what else? I guess that's it. So after this, we can write down the expression, that fundamental law. Right, so that's magnetic field at point P equals to mu naught nu constant divided by 4 pi, then the value of the current, then cross product between ds and r hat, and divided by the square of the distance from the segment to the point where we want to find magnetic field. So it's one of the fundamental laws, right, in physics. Of course, I should frame it. Again, it cannot be derived, so that's why I just drew the picture and wrote it down, because here nothing can be derived. Mu naught, permeability of free space, 4 pi times 10 to the power of minus 7 Tesla times meters divided by amps, right? Am I right? Yeah. Permeability. New constant, it's similar to epsilon naught. Epsilon naught described electrical properties of the vacuum. Mu naught describes magnetic properties of a vacuum. If this space around the wire were filled with some material, then instead of mu naught, we would use mu, but some constant which would describe properties of that particular material. Again, usually open the book and find the value of mu, because they all tabulated. Right? What else? Yeah. So direction of the magnetic field, basically, look, is determined by this cross product. Every time you'll have to look at the cross product to find the direction of ds. Oh, dB, direction of the magnetic field. Right? So what else? Yeah, units, of course, units of the magnetic field are units of B Tesla, named after a great guy, not after a car, right? Tesla. All right. Yeah, that's it about Biot-Savart law. We're going to practice. Maybe at the end of the class we will start looking at one problem. And now the last piece. Of course, this formula, this law, can be used to find magnetic field created by any wire, right? Any wire, just pick wire, right? So, and I can, of course, it can be complicated integration, right? But it can be done. And of course, what are the simplest situation? The simplest situation, what if you have a wire, straight wire, infinitely long, straight wire with current I. So what will be the expression for the magnetic field? At this point, we're not going to derive this. I did it once in 2014 in summer class, and students were looking at me like with big eyes because the integration is not that trivial. And after that, I stopped dragging students through that integration, right? So I usually just write down the formula. And the reason is because next class, we will introduce Ampere's law, and that formula can be derived in a much easier way. Right. So that's why for now I will just write the expression, the formula, which we will use, but we will prove it next classes. So now let me write, if you apply Biot-Savart law, Biot-Savart law for an infinitely long straight wire, for an infinitely long straight wire, then you will get, okay, probably let me first draw the system, draw the wire, right? And then I will write the expression. Probably I will write it here, draw it here, right? No, let me there. Right, so let's assume that this is my infinitely long straight wire, okay? With current, of course. Let's say this is current I, and let's say we want to find magnetic field at this point, right? So let's say it is at the distance d, perpendicular distance from the wire to the point in question. So then magnetic field B can be found using this formula, mu naught I divided by 2 pi d. It's a magnitude, right? Again, we will prove it. Again, as I said, it can be derived from this. But integration is not that trivial, so as I said, I decided to skip that, right? We will derive this formula next class using Ampere's law. The only thing which I don't like about this formula, that the author uses d. D, it's usually a symbol which is used to denote particular distances, right? Given distances. Usually R small is used, but for whatever reason, this author uses D, right? It's not the most convenient. Even in the next problem, we will run into some awkward situation about that. It's not a big deal, but okay, I don't want to elaborate about that. So that's the magnitude at this point, right? Then direction of the magnetic field. So first of all, you need to remember that magnetic field lines of the magnetic field created by this straight wire are circles. If you, for example, if this is if this is wire, right? If this is wire with a current, right? So magnetic field lines form circles centered on the wire. How can you get that? Oh, grab the compass needle and you can probe the magnetic field, right? So, but at this point, it's better just to remember, right? So they form circles. Magnetic field lines form circles centered on the wire, right? So let me draw a few circles of those. Right, so of course I can draw something like this, like that, right? So, okay, they're slightly distorted, but close. Right. Okay, circles. Then what about direction of these magnetic field lines? And in order to find a direction, we're going to introduce again a right-hand rule, and I usually call it right-hand rule number 2. Right-hand rule number 1 we used to find the direction of the cross product. Now it's right-hand rule number 2. So how do we use it? So let's assume again this is the wire with the current flows that way. So in order to find direction of the magnetic field lines, right-hand rule, on my right hand, then outstretch your thumb in the direction of the current and sort of curl your fingers around the wire, and your fingers give you direction of the magnetic field lines. Right. Again, outstretch your thumb in the direction of the current and curl your fingers around the wire. So in this case, in our case, so that's the direction of the current, and then my curled fingers gives us a direction of the magnetic field lines, sort of like this, right? Which is, let me try to, so it's this way, above it's towards us. All right, so this way. Right. So these are magnetic field lines. And of course, magnetic field, if you want to know, of course, tangent. Magnetic field is tangent to the magnetic field lines. Right. Okay, so now let me write. So this is direction. I mean, this is magnitude. Now direction, which we have wrote it. So now information about a direction can be found using right-hand rule number 2. I usually call it number 2 so that it's easier to refer and to tell you, okay, guys, you remember? Number 2 rule, number 1, so on. Right. Okay, so that's what we need for today's class. Mainly, we're going to play with this for today. Right? And then if we still have time, we can play with this formula. Okay, guys, if something not clear, just say it. Again, I'm checking if I mentioned everything. It looks like, yeah. So now, problem 14a. Because of these problems, I postponed the previous homework, 14a. So what do we have here? 2 wires parallel wires, but current flows in opposite directions. So wire number 1, wire number 2. In this, current flows this way. In this wire, current flows that way. Right? The same values of the current, and we will need to find magnetic field, net magnetic field at a particular point. Okay, so let me draw the situation. All right, okay, I'll probably draw it here. So let's say we have wire number 1. Okay, 1. And then, okay, let's say it blue, right? And green will be below. Wire number 2. And currents. Blue one goes this way, I, and the green one flows in the opposite direction. Right. So the value of the current, I think 10 amps. Yeah. 10 amps. Then some geometry is given, some distances is given. First of all, we need to find magnetic field at this point A, right? And that point is at a distance D. The value of D is also given. Let me check. 2 centimeters. Of course, at a certain point, we will have to convert into meters. Let's convert it immediately, right? To reduce chances of making a mistake. So it's 2 centimeters, 2 times 10 to the power of minus 2 meters. Then there is a distance between these wires also given. And that distance is given by L. Okay, L. L is 4 centimeters. Again, immediately into meters. So it will be 4 times 10 to the power of minus 2 meters, right? So that's it. That's what is given. And we need to find magnetic field at point A. In your homework, you will have to find magnetic field at point A. Then over here, somewhere in the middle, point B, and point C will be below. So we need to find B at point B. Wait, at point A. Force of habit, because usually we use P, but this time it's a point A. All right. Okay, so what? First of all, let's discuss physics. Physics is quite straightforward, reasonably simple. Any piece of wire create magnetic field. In this case, it's an infinitely long straight wire, right? So this wire creates magnetic field, which extends to infinity, fills up the whole space. And this wire creates its own independent magnetic field, right? So we have basically at any point superposition of two magnetic fields. But of course, we have to be careful because magnetic field is a vector. We need to add them properly as vectors. Right. Okay. And do we know the expression for the magnetic fields? Yeah, we just wrote it down. So this can be used for first wire and for the second wire. Right. And then direction. Yeah, direction, right-hand rule. So pretty much we have all necessary elements in order to start solving this problem. Right. So of course, I will first rewrite the formula. Of course, we will use mu naught I over 2 pi. And you see immediately I'm running into the problem kind of awkward situation, as I warned you before. D is usually used to denote a particular distance. And that's what we have here, particular distance, D, right? And use the same symbol in the formula. It's not nice, right? Usually, as I said, most of the books use R small. So let me also write down R small. So usually I see that there are some classic books, right? In physics, usually John Coley, and there are some other books, right? And the authors, in order to be different, they try to use different notations. Sometimes those notations kind of awkward or not convenient, right? It's one of those cases, right? Again, it's not bad. It's just slightly annoying. All right. Okay. So and then let's find directions of the magnetic field at this point created by the first wire and the second wire, right? Okay, the first one, blue one. Direction can be found using right-hand rule. Number 2, outstretch your thumb in the direction of the current and curl your fingers. Imagine easily, you should be easily imagine that direction of point A, magnetic field, direction of the magnetic field at point A will be out of the board. So imagine there will be a circle, or actually I can use this loop, right? So it will be something like this magnetic field line which goes through that point, right? And at this point, at point A, magnetic field will be out of the board, out of the board, out of the board notation you remember from the previous class. Out of the board, it's a dot with a circle, right? And let me use also blue color. So this is a magnetic field created by the blue wire, right? Direction of the magnetic field. Now let's do the same with the green. Again, you can imagine a different circle, right, for the green, of course, centered on the green. So right-hand rule, outstretch your thumb in this direction, right, and curl your fingers around the wire, right? So in this case, magnetic field will be into the board, right? So into the board, it's a cross. Circle with a cross. So that's the magnetic field, right? Okay, maybe I will write B2 because it's a second wire, and this is B1. Right. So you see, magnetic fields at those points are in opposite directions. Maybe you know what, since it might help you with your homework, let me also draw magnetic field line directions for the rest of the space. Blue. So above this wire, magnetic field is out of the board, so that way. But below, of course, it will be now into the board. Below the wire 1, of course, magnetic field will be into the board. So into the board, cross. So between the wires, magnetic field B1 will be into the board, and of course, even below this, right? So because this magnetic field fills up the whole space. So even below this, it will be still B1 pointing into the board. Sometimes students get confused at this point, at this stage, right, about the directions. Right. Okay, now let's do the same with the green. So Above the green wire, magnetic field is into the board, so cross, even here cross, it's still above the green wire, so magnetic field still into the board. So this is B2, but once you go below the green wire, again, loop, imagine the loop, right? So if this is into the board, then here it's out of the board, right? Below the green wire, magnetic field now will be out of the board. Out, it's a dot. Okay, so this, of course, will be useful for your homework. Okay, but we still need to answer the question about point A. And let me introduce coordinate system. Let me introduce coordinate system, and let me introduce z-axis, z-axis out of the page, out of the board. Yeah, z. Right. Why? Because I want to write the final answer in terms of unit vectors. Of course, you can write it in terms of in and out, right? It's also okay. But I want to use unit vectors, right? So if this is z, then of course this will be x-axis, and that will be a y-axis, right? Okay, so now let's write the net magnetic field. Maybe I can even write first this. All right, so the magnetic field B1, I can write it as what? Mu naught I over 2 pi. What's the distance instead of r for B1? It's a distance, perpendicular distance from the center of the wire to the point in question, to the point where we want to find magnetic field. In our case, B1, it's this distance, R1, right? So this distance, maybe I can show that this is distance R1, so which is equal to D, right? But first, let me write still R1. In direction, you see magnetic field B1 out of the board, and my z-axis also out of the board. So plus z hat direction. I just want to be fancy and write in a vector form. And then very similar, I can write for B2. Of course, it will be mu naught times I divided by 2 pi. And what is R2 now? Distance from the second wire to the point where we want to find magnetic field. It's at this distance, right? So this is R2. And of course, R2 will be equal D plus L. Basically, everything is given, right? And the direction of B2 is out of the board. I mean, into the board, and this is out of the board, z-axis. So it's a minus z hat, right? Okay, so now let's add them up using principle of superposition, right? So B net will be B1 plus B2. Okay, now so let's write explicitly instead of R1, it's a D, and R2, it's a D plus L. So it will be mu naught I over 2 pi D Z hat, right? And then plus mu naught I over 2 pi D plus L, and in a minus Z hat direction, right? So basically it's done, right? Because everything is given, mu naught I, D, L, right? So we can, of course, we can make it look nice. We can factor out mu naught I divided by 2 pi, and z-axis, unit vector in the z direction. And what will be inside? 1 over D minus 1 over D plus L. Okay, so that's the answer. But again, if you don't like introducing that coordinate system, of course you can talk about in and out. Yeah, I see some students sometimes do it. Okay, it's okay as long as it's clear what you've done and how you've done it. All right, so I'm not going to plug numbers. The answer will be 6.7 times 10 to the power of minus 5. Direction z, positive z. And of course, units of Tesla. Units of Tesla. A few times I give a problem like this on the exam, and usually students don't have significant troubles. Of course, anyone who practices a little bit. It's one of the easiest. Okay, so if something not clear, please express yourself. Make some sounds. All right, so now next one. The next one is not from the book. I will just put a new bullet, or maybe even separate with a straight line. Right? And it's effectively the same system, right? Two wires, right, parallel. But now let me grab the top wire and turn it by 90 degrees. So now we see we have this situation. And we will have to find magnetic field at the midpoint between these two wires. And the values of the current are going to be different. Right? You see, the difference, so we just grab the top wire and turn it by 90 degrees. Okay, so how can I draw that? Blue, okay, the top one. All right, so, and the blue one, actually, I turn it that way, right? So that current flows towards us. Okay, and towards us, it's a dot. So let's say this is wire number 1, and current I sub T. T stands for top wire, 20 amps. Then the bottom wire is, the same. And actually, direction is also opposite direction of the current. It's not a big deal. So let me take it and draw it here. And direction, as I said, it's this way. So I sub B equals to what? 12 amps. 12 amps. So that's situation. And of course, we need to find now magnetic field at the midpoint. Right. So let me draw that this distance and this distance are the same. All right, so let's say this is LT 10 centimeters. The distance from the top wire to the point where we want to find magnetic field, 10 centimeters, 0.1 meters. And the same distance from the bottom wire. So let me write L sub B. B stands for bottom, 10 centimeters, right? So basically, that's what is given, and we need to find magnetic field. Let me put a big dot and write, so we need to find magnetic field at that point. Physics, exactly the same, right? So we have just two magnetic fields, which fills up the whole space. And at any point, it's a superposition of two fields. But again, we need to remember, magnetic field is a vector. We need to treat them as a vector. I will show you the point where tons of mistakes lots of students make that mistake. Again, in terms of formulas, we just need to use this twice for the top wire and for the bottom wire. But we have to be careful with directions. Let's draw the direction. Again, right-hand rule number 2. Let's start with the top one. So a current flows out of the board. So outstretch your thumb out of the board. So it will be like this, right? And then curl your fingers around the wire. So again, magnetic field lines form circles. So it's like this. So over here, of course, magnetic field this way, here this way. But at the point in question, magnetic field will be pointing this way, right, towards me. right? So magnetic field, blue, okay, let me use also blue color. So this will be B sub T. Again, T stands for the top wire. Agree? Just the right-hand rule number 2, usually much easier, and most of students are comfortable with that. Again, outstretch your thumb and curl your fingers. Now the bottom one, it's the same situation like here, right? So outstretch your thumb in that direction and curl your fingers. So of course, above the wire, above the green wire, of course, my fingers are out of the board, giving me a direction of the magnetic field out of the board, dot. So it means that I can draw this green circle with a dot. So this will be B sub B. B stands for the bottom, right? So we have these are two directions of the magnetic fields, right? So you see, they are perpendicular to each other, and that's what most of the students missed on. If I give a problem like this on the test, they just find magnitude of using this formula of the first wire, magnitude of the magnetic field, second wire, and just add them up as if they were parallel to each other. No. Let me even redraw the top view, right? So in order to see what needs to be done, right? So let me write top view, right? So magnetic field BT, it's that way. So let me draw it. B sub T, right? And then B sub B, okay, it's a top view, so it's towards us. So I will draw it just below, lower, this way. So this will be B sub B. So that's what we see. And now if we want to find the magnitude, okay, first of all, let's draw the direction of the net magnetic field, because that's what we want to find. Net magnetic field, of course, we need to draw this parallelogram. And this will be our B net. And usually the question is find the magnitude of the magnetic field, net magnetic field. So now you see what needs to be done. You need to apply Pythagorean theorem. And this is the point where lots of students, they skip drawing the nice picture. As a result, they just add magnitudes. And of course, that doesn't make any sense, right? That's why I usually encourage you, draw a nice picture, because pictures help. Pictures help a lot. Okay, so now I think for everyone it should be clear that in order to find the magnitude of B net, so you just need to take BT squared plus B sub B squared and take a square root. And of course, magnitude of BT and BB, yeah, we can find using this formula, of course. Okay, let me write explicitly, of course. Will be square root of mu naught I sub t divided by 2 pi. Then distance from the wire to the point in question. Of course, distances are the same, but let me still use L sub t and L sub b. L sub t, and the whole thing is squared, and then plus, very similar for the second wire, mu naught I sub b divided by 2 pi L sub b. L sub b squared and square root. Okay, so everything is given. Of course, you can factor out something, right? And of course, I will probably skip that. And you will get the answer. I will just write down the number. So it will be equal to 4.66 times 10 to the power of minus 5 units of Tesla, right? After Nikola Tesla Okay, again, as I said, usually problem this one, most of students do it. Yeah, successfully. Very successfully. In the second, they're perpendicular, so you have, of course, you have to draw diagram and use Pythagorean theorem. Of course, directions will be slightly more complicated, but still possible. Right. But usually I ask for the magnitude. Okay, so these problems you needed for the previous homework. That's why I postpone it till Wednesday. So you still have till Wednesday to finish that homework. I think it's number 8. Right? Okay, so the next problem is more complicated than this. Right? So in the next problem, we will have to use, yeah, this, and we will have to do some integration. I will start it today. We will just discuss the problem, and we will continue it next class, right? And then next class also Ampere's law. Okay, I need to erase the top problem. So this problem 46. And then next class I will just draw the problem, the picture in advance. Right, so 46. And I think it's also in your homework. So we have a loop with current and loop of a complicated shape, reasonably complicated. So which consists of two semicircles of different radii and some sections connecting those two semicircles. Okay, let me start with the first one, with the larger one. Okay. So that's the outer semicircle. Then there are pieces connecting. And then the semicircle with a, okay, not the best picture, but every time it's not the easiest drawing, right? So that is the center of both semicircles and two radii given. So let me draw it first here. So this is R, okay, R1, and no, this is R2. Sorry, this is R2. And this is R1. Given R2 equals to 2 centimeters and R1 equals to 1 centimeter. Then, as I said, loop, yeah, it's a loop, you see, made of wire. And there's a current flowing. Current is in this direction. So I, and the value of the current, of course, given 5 amps. I equals to 5 amps. Then what else is given? I think that's it. Radii, current, yeah. And of course, now the question, we need to raise the question. We need to find the magnetic field at this point. I think I label it P. Yeah. Let's say this is point P. So we need to find, find magnetic field at point P. Why that point? Because it's an introductory level course, right? And relative to this point, the picture is quite symmetrical. If somebody asks you to find the magnetic field, for example, at any other points except for this, right, that person obviously just hates you, right? Because in that case, you would struggle a lot with calculation, I mean, with calculus, right? So this point P, yeah, it's nice, right? And problem can be solved within like 15 minutes. Okay, so pretty much that's where we will continue next class. Right. Again, I will prepare a picture in advance, so I will not have to repeat all over again. Right. And of course, yeah, as I said, we will have to use Biot-Savart law, and we will have to do integration. But you will see that integration is not that bad. Will be reasonably easy. But of course, you have to carefully look at each term. What's the meaning, right? What are the directions, and so on and so forth. Right?